And now if you apply this to W, that means the integration over the whole domain of divergence of the definition of W, which is the gradient of U times V, is equal to the boundary integral of a normal dot with gradient of U times V. Application of divergence theorem. And further, you can expand the divergence on the left-hand side. Okay, what is the divergence of a vector times scalar? Well, it's not obvious, but like you can do this with it's just the algebra of using the rule, the chain rule. You can obtain that this is equal to the divergence of the gradient of U times V. So now I pull this V out of this divergence plus the gradient of U times the gradient of V. So that's application of chain rule. You can do this by expanding the both divergence and gradient into partial x, partial y, and then apply the chain rule systematically. Okay, so this is going to be equal to this boundary integral. And remember, this term is what we have in the Poissons equation after the projection. We have this divergence of gradient of U times V, right? So we can write this term only equal to this boundary integral minus this part, minus divergence U, divergence of V. All right, so this is what we call integration by parts in multiple dimensions. All right, have you encountered this before? You have? Nice. Okay, good. So yeah, so most of us have encountered integration by parts in 1D, but like in multiple dimensions, you can derive that from divergence theorem. Okay, now we apply this onto the projected Poissons equation. Okay, and we are going to see that after this inequality, the left-hand side has a double derivative, and the right-hand side has no double derivative. We're essentially removing the one layer of requirement of differentiability from U and putting that requirement onto V. Now, V needs to be, so before this, V has no requirements on differentiability. Now, V has a requirement on differentiability, but that's fine because our space of U and V are actually the same. They have the same differentiability. Okay, now that means the Poissons equation can be written as first of all, I get this thing, right, and minus this thing, and minus integration of f times v equal to 0. So that's my new Poissons equation. That's my new Poissons equation after I project it onto a space where V is a member of the space. And V is a member of the space where satisfies the boundary condition of V equal to 0 at the boundaries. So the first term becomes what? The first term is gone, right? The first term is gone because V at the boundary is equal to 0. All right, any questions? Please raise any questions. If any derivation is not clear, please ask. Any questions? No? Okay. Right, so the first term is gone, so I'm only left with the second part. So I'm only left with the part that grad u dot grad v times dx plus f v dx is equal to 0. That is my new Poissons equation. And we are going to see later on that we're going to generalize this to that this is a more finite element friendly version of the differential equation. Okay, this is called the weak form of the differential equation. So the weak form is derived by taking the differential equation, project it onto some space, and do some integration by parts. The purpose of the integration by parts is to weaken the requirement on how many derivatives can I take on the solution U. So it is the same as, so basically this weak form is the same as the original differential equation if the solution satisfies like second order differentiability. But it is weaker because the weak form doesn't require you to satisfy second order differentiability. You can obtain solutions. For example, if f is a delta function, when f is a delta function, there is actually no solution to the differential equation in the strong sense. But in the weak sense, I can get a solution even f is a delta function. All right, so this is the weak form. This is the weak form. This is the weak form of the differential equation. Okay, so once we have the weak form, we can derive how to proceed by substituting the basis of the space into both U and V. Okay, so let's copy the weak form and substituting the basis. Oh, that's not, is that no? That's too thick. I want a pen. Okay, so the weak form is grad U grad V dx plus f v dx equal to 0. Okay, so I'm going to substitute two things. I'm going to define a basis that is phi1, phi2. Okay, let me take a look at this in our case. In our case, remember we have a collection of triangles, right? We have a collection of triangles that can be pretty large. We want a basis for the space that is continuous and piecewise linear. Okay, and we said if we can define the value of this function at all the nodes, then that function is uniquely defined, right? Because inside every triangle, that uniquely defines a linear function. So if we can define a basis of the values at the nodes, then we basically have defined a basis for this linear for the space of all these piecewise linear functions. And the basis of the value at all these nodes can simply be the set of values that are equal to 1 at one of the grid points and 0 anywhere else. So for example, if I take the value equal to 1 here and 0 anywhere else, okay, then at these triangles that doesn't contain this one node, what would the function look like? Yeah, for this triangle, all the three nodes are equal to 0. If I require it to be a linear function, yeah, it has to be 0 everywhere, right? And also the function is 0 over here and 0 over here. It is only non-zero in a triangle that has a node that is non-zero. Okay, and the contour of that function would look like this as it goes higher and higher towards 1. And in this node to be like this. It's continuous, so I mean these are supposed to, the contours are supposed to be also continuous. And in this triangle, it should be like this. Now this triangle, it's like this. And in this triangle, it's like this. All right. So it's like a tent, as somebody said in the beginning, right? It's like a tent that has the highest point here and is 0 when it gets to the outside of the triangles. And it'll stay 0 everywhere else. I can define such a tent function for every single node that doesn't lie on the boundary. If it lies on the boundary, then I don't need that because it satisfies the boundary condition, right? Okay, so I can define these spaces 1 to n, and n is the number of node points in the interior of this mesh. After I define the spaces, I both write u and v in terms of a linear summation of the bases. So u becomes a summation I goes from 1 to n of ui times vi, which is a function of x, and ui is just becomes a number. It's no longer a function. And also, v can be also written as a summation of these basis functions. So, as long as this equation is satisfied for each one of these members of the basis, this equation is satisfied for any v. So v can also be written as a summation of these bases, which means if I can have this satisfied when v is equal to each vi, then the linear combination of these n equalities is going to give me an equality for any v. I only need to enforce the equation for v equal to each vi, I equal to 1 to n. All right. Okay. By doing that, by doing these two things, right? By using the fact that the xh is finite dimensional, I can reduce this equation from an equation with the continuous functions u and v to equations with these numbers ui. So doing that gives me, the first term becomes integration of a summation of ui times gradient of vi. Let me actually write this as j because, again, I don't want to have the indices to conflict. Okay, so u is expanded using I and j. So vi dot with grad of vj dx plus integration of f times vj dx is equal to 0. Or I can pull this summation out of this integral, and I can pull this ui out of the integral, right? Because these are just numbers. Okay, so basically, again, this can be pre-computed, and this can be pre-computed. And the left parenthesis has two indices, I and j. It becomes a matrix. This only has an index j, it becomes a vector. And my ui can be solved by solving a matrix equation. All right, this is how it'll work. Any questions so far?